Hello, my name is Mathis Rieke, and in the following few minutes I will present the work carried out on aviation service performance testing within the OWS-9 testbed. In previous testbeds, the focus lied primarily on the realization of functional requirements. Performance and stability related aspects of services have not been assessed. The aim of this study was on the one hand the overall evaluation of the aviation service architecture, and on the other individual performance and endurance assessments of the involved services. To achieve these goals, an approach has been designed and realized which provides comparable test results across different service vendors. Besides service testing, the identification of possible architecture adjustments was another outcome of the study. Let us just start by initiating and executing a WFS test model. Here you can see the user interface of the developed performance tool. In the first step, we select the WFS GetFeature Model. The user can specify the service URL and a set of model-specific parameters. Let us adjust the identifier of the feature we want to retrieve. Also, we adjust the testing period to 5 minutes. If necessary, the user can specify a password for services which require authentication. Finally, we start the execution of the test model. We quickly receive a first result. Let us come back later to inspect the results of our model execution. The foundation for the assessments of services are a set of abstract test models, which are based on the commonly used interface methods of the aviation web services. Abstract test models allow use case-specific adjustments while not changing the general behavior. The following 3 types of abstract test models have been developed. WFS GetFeature models with realizations to retrieve all time slices of an airport heliport for a given valid time and retrieve all airport heliport features which match a designated pattern. WFS Transactional Models with realizations to insert a baseline perm delta and a corresponding correction and insertion of a temp delta time slice. Event service test models for endurance and performance testing with individual service setups like varying number of subscribers and denotem messages. Let us take a closer look at the workflow of these 3 test models. As the first step, the WFS GetFeature model initializes all needed requests with the user-defined parameters. It then starts to execute these requests in a cyclic manner for a defined testing period. After every request execution, several parameters of the response, such as the number of returned features, are evaluated and stored. Much the same as the GetFeature model, the WFS Transactional Model first of all initializes the used requests. The execution part of the transactional model is designed in alignment with the AXM5 temporality model. In the first step, a commissioning is inserted into the WFS. In order to clean things up and leave the service in the same state as prior, each insertion is followed by the insertion of a cancellation. Both the commissioning and cancellation are taken into consideration in the response evaluation. It extracts several parameters such as the number of inserted features and the measured response time. The event service model is designed in a completely different way compared to the WFS test models. As the event service provides publish-subscribe functionality using push-based communication, the round-trip time of a denotem needed to be measured. A round trip starts with the push of a denotem to the service and ends when the same denotem arrived at the dedicated consumer endpoint of the performance tool. The execution is applied in a cyclic manner for a defined testing period similar to the WFS test models. The evaluation extracts a set of parameters such as the mean round-trip time and the total number of received notifications for one execution cycle. As a final step, all previously created subscriptions are removed from the event services. 2 service test environments have been defined in which both the test models are executed with the same set of parameters, the remote and the local environment. The remote environment is designed to simulate the general aviation service architecture. Web service and performance tool, acting as a replacement for a client, are physically distributed. In the local environment, both the tool and the services are hosted on the same network. This helps to minimize network-related influence on test results. As previously seen, the performance tool is a web-based tool running in modern browsers using JavaScript. It implements the Servlet2.x API, thus being deployable in common servlet containers such as Tomcat or Jetty. It allows long-time model executions as user sessions are stored and can be accessed via permalinks. It is written completely in Java and provides interfaces and abstract classes for test models, though it is not limited to the previously presented WFS and event service models. The user interface is created dynamically based on the parameters of the model. The tool provides test results in various formats: comma-separated files, raw session logs, and chart diagrams. Let us now check for the results of the model we have executed a few minutes ago. All results provided by a model execution can be accessed through the dedicated Results tab of the user interface. This graph illustrates the results of the WFS GetFeature Model. All introduced test models have been executed against the service instances of the different vendors. Test results have been anonymized as the services were not settled in a production environment. Here we see the results of a WFS GetFeature model. It shows some performance peaks, but the general mean response time is less than 1 second for both WFS vendors. The returned feature count is stable for the complete testing period, which indicates a stable service instance. The WFS transactional results also show some performance peaks. The response times are higher compared to the GetFeature model. The cause lies in the more complex nature of a transactional request. All requests executed successfully, as indicated by the stable count of inserted features. The event service test results highlighted in this diagram show variations among service providers. The hole in the left-hand result indicates a possible unreachable server due to networking issues. In general, the event services showed limitations when more than 200 simultaneous subscribers had been registered. This led to message jams, an unstable dissemination of messages, and long response times. Within OWS-9, a general approach to assess the performance of the aviation data provision services has been developed. The design of service-specific test models allowed the execution of tests for use cases common in the aviation domain, including WFS GetFeature and Transactional models, as well as event service subscription models. Two different test environments have been designed to allow better assessment of the test results. Based on the developed test models, a prototypical implementation has been accomplished. This allowed the reproducibility of test results as well as the provision of high-level results such as graphs. Test results have been created which are comparable across all service vendors. Finally, I would like to thank you for your interest in the aviation performance study work. Detailed test results and additional insights are provided in the OWS-9 report on aviation performance study.